Welcome back. Hope you're refreshed and raring to go. And no, I'd rather be on break still. I understand. But today is a question and answer day. So 3.5, 3.6, 3.7, implicit differentiation, applications, and the chain rule? No, logarithmic differentiation. What questions do you have for me? Yes, Sid.
How far do we go to like simplify it? Like, how do we want it?
Well, that depends on what we're doing, right? If it just says take the derivative, don't bother. Once you're done, stop. You've taken the derivative, you don't need to simplify at all. But if you want to do something with the derivative, you're plugging something in, simplify it to where you think it's easiest to plug into. You're setting it equal to something. Well, then I want to set it so that the algebra is as simple as I can do it to make my life easier for setting things equal to zero, which means I want to try and put things on a common denominator, set things so that they are all in terms of simplified trig functions. If I had cosecant, secant, and tangent, I probably want to turn everything to sines and cosines because it's easier to set those equal to zero. So it's going to depend on what I'm going to do with the derivative I get. I'd love to say there is an absolute rule. There isn't. Unless the instructions are specific. It says don't simplify, do the derivative, walk away. You're welcome. Other questions? Oh, hang on. I will have one specific. In our logarithmic derivative set, the logarithm at the end, at all the way at the end, I have y prime equals, right? That whole thing should be explicitly in x. If I started with an explicit equation, even if I have to do a logarithm along the way, I should end with an explicit derivative. Like when we did x to the x as our example in class last week before. So if I have this, that's an explicit function. If I go through the process of doing the logarithmic derivative, the first thing I do is I put a log on both sides, then I take this out. When I take the derivative on the left, I have to use the chain rule because that's a function of y and I'm taking my derivative in x. So when I take my derivative in x, this side becomes 1 over y dy dx. There's my chain rule. But over here, I do the product rule. My goal is to find dy dx, right? So the last step is to move that y over there. While that answer is correct, I would go one step further. Because I started with an explicit equation and my result is an implicit equation with x and y mixed together. Here, I would go so far as to resubstitute. That's the only simplification, quote unquote, that I always do. More questions? Yes, Chris. Yeah, one of the. Yeah, absolutely. Pick something. Let's see. So the application's 10, 16, 26, 34. 10 is about a thrown ball. 11 is very similar. 16 is about a stone dropped in a lake. 17 is very similar. 26 and 34. 26 is a chemistry problem. 34 is a cost function. Which one do you like? Say again? The chemistry one. Okay, so 26 is the chemistry one. We can do 25, or we can do 25 is very similar. We'll do 25. So 25 gives me Boyle's law for gas compression. When a sample of gas is compressed at a constant temperature, the product of the pressure and the volume remains constant. Doesn't help if you can't see it because I have other crap in the way. There we go. Find the rate of change of volume with respect to pressure. Okay. That phrase, with respect to pressure, means I'm treating P as the variable that is independent and V as the dependent variable. So it's kind of like X and Y, but I've said it's with respect to pressure, so it's with respect to P. You have two choices on how you can do this. You can leave it like this, or you can rearrange. Is this function able to be written? V equals? Can you rearrange it to get V all along? Exactly. So I start. Now that C is a constant, so I might as well, I can leave it like, or I could write it like that. Because it's in the bottom, it's a -1 power. I want the rate of change of volume with respect to pressure, that is a derivative. And it's the derivative dV dP. Since my right-hand side is in terms of P, that's perfect. I can take the derivative. What do I get over there on the right-hand side? Okay, the C is going to stay there. And then -1, keep going. What do I do with that? Unfortunately, no, because this is like an X to the -1. It's a power rule. So I need to treat this like a power rule. So what do I do with the power rule? I bring this down front. So that stays. And then what do I do to the power? Right, I subtract another one. I could write that like that as well. Negative powers go in the bottom. I don't have to. Fiona, this is another case where simplifying is optional completely, but I think this is easier to look at than this, simply in terms of the way I understand what's going on here. I think it's divided by p squared. That means it's getting small as p gets bigger. And think about this for a second. If my pressure goes up, what's going to happen to my volume? When I multiply the two together, I get a constant. If the pressure gets bigger, the volume has to get smaller to match those two together. So that when I multiply, I get the same answer, right? If one of them goes up, the other one has to go down to keep it the same value. A sample of gas is in a container at low pressure and is steadily compressed at constant temperature for 10 minutes. So we are at a low pressure. So I'm at a low pressure to start. Begin compressing. Without letting the temperature go up for 10 minutes. You'll notice there's nothing about time in this problem at all, is there? So I don't care about the time, except to say that I know I'm compressing, right? So at the beginning, the pressure is low. At the end, the pressure is higher. I don't know if that's a lot higher or a little higher, but it's higher. Now, is the volume decreasing more at the beginning or at the end? Huh. They didn't give me any numbers. They didn't give me any numbers at all. So let's make some up. At the beginning, give me a number for our pressure. All we know at the beginning is that the pressure is low, right? Well, 1. At the end, give me a number for our pressure. Say again? 50. So it went from 1 to 50. That's a big jump, right? It went up. Let's look at our change. I copied down the formula, so I still have it. Let's plug in our two numbers. Here, dV/dP is negative C over 1 squared, but 1 squared is just 1. Here, dV/dP is negative C over 50 squared. What's 50 squared? Really big. So here's my question to you. I don't know what C is. It doesn't help at the moment whether or not I know what C is. Which of those two changes is bigger? Which is smaller? This one is smaller since we're dividing by a bigger thing. So at the end, I have smaller change in volume than at the beginning. Is the volume decreasing more at the beginning or the end? Well, you just told me there's less change at the end than there is at the beginning. I put larger in quotes here because technically this number is going to be more negative than this one. So I want to use the word smaller, but it's larger in value. Does that make it better? So we are decreasing more at the start. Hey, wait a second. I've done this before. I am pumping up a ball or a tire on a bike or on my car, right? Going down to put air in my tires, right? At the beginning, the volume changes more as we start from a flat tire and start putting air in it. But then as it gets full, it gets harder and harder to put the air in, doesn't it? So we actually change the volume a little less as the pressure gets more. As we keep pumping, we add less and less to the volume by increasing the pressure. Prove that isothermal compressivity, I beg your pardon? See example 5, is given by beta equals 1 over P. So now I go back and I look at example 5. And example 5 says one of the quantities of interest in thermodynamics is compressibility. How much can you compress stuff? If a given substance is kept at constant temperature, then its volume depends on the pressure. Well, that's exactly what we were just talking about with this rule. Hey, that's exactly what we came up with, wasn't it? Well, I'll be danged. So that proof is recognizing this is what we were just looking at. Better? Please notice I didn't require numbers to do any of this. I can make them up, but this sort of thing would work with any two numbers that I put in as long as I knew that the end number was higher than the beginning number. By the way, the constant temperature thing here is actually beneficial to us because pressure and volume and temperature are all related. The ideal gas laws, who's taken Gen Chem 1? Oh, okay, a couple of you. So we had, what did he call this one? This was Boyle's law. There's also Charles' law, which says that volume is related to temperature. If I put the two together, I get pressure and volume is some number times temperature, which means that pressure and volume are inversely proportional to temperature to give me some constant. This, by the way, is based on a molar number of moles of the gas and a constant discovered by Boyle and Charles together. If I take a cylinder of gas and I squeeze it really fast, compressing the volume, increasing the temperature, I can start a fire. They sell as camping equipment a plastic plunger about this big with a really tight seal at the top. All you do is you take a little piece of tinder, shaved wood or cotton ball or something, put the plunger over it, whack the plunger down really hard. It compresses the air, it raises the temperature, it flashes the cotton, and it makes a spark. It's a fire starter. And all it uses is this idea. It's calculus in action. Anyhow, the peas and the vegetables are on the table. PV over T. That's how I remember that. I learned that in 1983. I haven't forgotten it since. Anyhow, more questions. Chris, I would also point out to you that there is this problem, number 29, which doesn't give us a function this time, but it gives us a table. And when we get this table, we don't actually get a tangent line, we get a bunch of secant lines. But I can at least approximate my rate of change using the information in the table. This actually is what happens more often in a lab, is that we take discrete time measurements, how fast is something changing, look at it over time, and then approximate our derivative that way. A number of years ago, a student asked for help on a research project over in the lab. They were looking at plant digestion of sugars, an algae digesting sugars. All right, I'm going to be a bad chemist. I don't remember which is which. There's a fructose, sucrose, and glucose. Two of those are simple. One of those is compound. I know glucose is simple. Is sucrose simple or is fructose simple? I can never remember which is which. I'm going to make it up. The one sugar gets broken into two. But the plants, like the algae, likes eating glucose more. So, if the algae starts to break down the glucose, before it starts to break down the sucrose, glucose and sucrose are chiral molecules. They're handed, they have direction to them. One of them is right twisted, the other one is left twisted. When you shine light through it, the light bends based on how much sugar of each type is there. If they're equal in amount, then it ends up balanced. But as more glucose gets eaten, the light starts to twist to the left, because there's no right from the glucose to turn it back. And then it'll turn back as it eats the other one. And so the question was, how fast is it converting 1 to 2 and then eating the first one before it starts to eat the second one? This is the same sort of chemistry question as our reaction question here in number 26. How fast is the reaction occurring? So what this student did was they set up in the instrumental lab over on Lynch Hall, they set up an optical polarimeter. It shines a light through a sample of liquid and measures the polarity, the twist in the light. And she set it up, and every hour she measured the twist. And we plotted a curve and fit a function to the plot she came up with, so we could take derivatives. We then approximated those derivatives with her data first, fit the function, and then checked how close we were. I thought it was really cool. But I know this much about plant chemistry, so I was just happy to do the number crunching. More questions? So there are two rules we need to remember when dealing with logarithms. The first is that the derivative of a logarithm comes from doing implicit derivatives. If I think about the way I'm going to do the derivative of this equation, well, I might as well rewrite it because I don't know how to do ln, but I know how to do e to the y. So I take the derivative over here. The derivative of x is just 1. The derivative of e to the stuff is e to the stuff. But wait, there's more. My chain rule comes into play. The derivative of y is dy dx. But since my goal was to find dy dx, I end up with that. Now, here's where the comment I made to Fiona earlier comes into play. I don't like having an implicit form when I started with an explicit form. So I take that e to the y and I swap it back. And I get dy dx is 1 over x. So whenever I am dealing with a logarithm in my problem, I'm going to get a 1 over. Now it's just a matter of inserting this knowledge with other rules, right? So if I had this, I can do the product rule. But the product rule with the derivative of the ln, right? So product rule says I do the derivative of the first, leave the second alone. Then I leave the first alone, do the derivative of the second, and there's my derivative. Again, simplification is not required, but that's going to cancel, isn't it? That's easier to work with. I can also use the chain rule with the ln. Right? Well, the ln of x is 1 over x. So ln of stuff is 1 over stuff. But wait, there's more. What goes in that set of parentheses? There's a formula sheet. I don't have to have all those trig derivatives memorized. There's a formula sheet. It's at the end of our second exam review. It's attached to the exam. So I can grab it and say, oh, the derivative of secant. There it is. There's secant to secant tangent. Hey, what nice thing happens? That's convenient. Chris, that also leads me back to that first problem because I said, hey, I've got that x to the x. I don't know which way to do it. But if I put an ln on both sides and I pull this power out, that's properties of logarithms, right? A power gets put outside, multiplying becomes adding, dividing becomes subtracting. I can make my life easier by using a logarithm. And that's what I did here. So that's my logarithmic derivative, but it's basically using this chain rule idea for ln. More questions? Chris, that was Thursday before break, right? Yeah. So the notes and the video are on the YouTube channel. The notes are on our Kansas page. You can watch the whole thing. More questions? Okay, a reminder. Saturday is one of my favorite days of the year, this coming. What's the date, Saturday? It's March 14th. It's Pi Day. Now, there were very many celebrations of Pi Day that we have had here at Seton Hill in the past, but since it's a Saturday, I can't do what we usually do, which is sit in the cafeteria and let people throw pie at me. I have pictures. It's happened. So Wednesday, there is a calculus competition. If you're in Calc 1, this is the stuff we do at the end of Calc 1. So you should come and watch. But if you know anybody who's in Calc 2 or in other classes, you should hook them and get them to do this stuff. Friday, we'll be doing, you know what a haiku is? Okay. It's syllable count, right? So we'll do a paiku. 3 syllables, 1 syllable, 4 syllables. 314, right? There'll be a pi contest if you can recite the digits of pi. Our winner last year came up with 150 digits from memory. I don't think he's competing this year. There's a trivia contest, several points throughout the day. In addition, the winner for this one last year had one for his second time. I don't mean to put pressure on you, but Griffin, the man who won this, is blind congenitally. He did the entire set of problems in his head and won 2 years in a row. I want to see somebody because he's graduated. He's not here. We need somebody to take the championship. Anyhow, that's later this week. If you don't have any other questions, I don't have a reason to nail your butts to the chair. I will see you all on Wednesday.